Now let's switch our attention to equivalent martingale measure. So before we talk about that, we have to talk about what is a martingale. So basically, loosely speaking, martingale is just a term that says if you have a stochastic process, and if you take expectation, let's say the stochastic process for x, and x takes different values at different time points. So if you take expectation of x conditioned upon some earlier value, so in this case, you have x at time t naught, t0, and if you take a conditional expectation, an expectation of x of a future time t conditioned upon this earlier time x0, then this expected value is just x0. So if a stochastic process has this property, then this stochastic process is called a martingale. And we will see that a Wiener process is really just a martingale, because you can take the expected value of a Wiener process, and condition upon an earlier point that the Wiener process is at. The conditional expected value will just be that earlier point, because the expected change conditioned upon that earlier value is 0. Therefore, the expected value at a future time is just the value at the earlier time, conditioned upon this value at the earlier time. The conditional expectation will give you this x naught. To analyze this issue further, basically to look closer into equivalent martingale measure, let's approach this question with a technique similar to what we have discovered before. So before, recall that we constructed a portfolio. That portfolio has no random part. The change of the portfolio value has no random part. And we say that that is a risk-free portfolio, and the change of portfolio value is equal to R times the initial portfolio value dt. We can try an approach very similar to that. Let's say, suppose we have two asset price processes, depends on the same random factor. So for example, you have a process F and follows this stochastic process. dF is equal to mu F, mu is some parameter, mu F times F dt plus sigma F, another parameter, times F dz. And this is the Z is the Wiener process. And another asset process is dg. G is another variable. And dg follows the process mu g times g dt plus sigma g times g dz. Okay, now here you should notice that both of them have the same, it's driven by the same Wiener process, Z. They're the same Z here. Okay, so they have the same random factor that's drive the changes. Here is the expected value. So your mu F is different from mu G. Sigma F is different from sigma G, but they are both under a function of this particular Wiener process Z. Okay, so have the same random factors. Now, in this case, you can think about it as F and G. Let's say F is a stock, G may be the option of a stock. So they're all both driven by the same random factors, or they're, F and G are both options on another stock. Okay, so again, they're driven by the same random factor based on the underlying asset. Now, the question here is, if we have F and G that are like this, what is the relationship between them? Okay, what are the things we can derive out of that? Well, we can see that by, again, forming an instantaneous risk-free portfolio. The way we do that is we long sigma G times G unit of F and short sigma F times F units of G. Okay, so here is sigma G, but it's number of unit times G and number of unit of F, and here's F, related units of G. Okay, so if you do that, so you basically have a portfolio like this. And by Ito's lemma, you can derive, you can look at your portfolios, the change of the portfolio's value basically is the change this part df, then this part dg, and dg df follows the process that we mentioned earlier. Well, if you put them through and you write them out, you will see the dz part is canceled. So if the dz part is canceled, you only left with the dt part, and this is deterministic. So you have a risk-free portfolio. So d pi then must equal to r times pi times dt. Because it's a risk-free portfolio, must receive risk-free rate of return. Otherwise, there'll be an arbitrage. So to avoid any arbitrage, that must be the case. So if that is the case, then we have basically this thing here is equal to r times this. Okay, then if we rearrange, we will find out that basically mu f minus r divided by sigma f is equal to mu g minus r divided by sigma g. So you can, well, we're talking about two, but if you do similar things, you can have a number of those ones. So they all, if it's drift minus the risk-free rate divided by the volatility, it's just going to be a constant. So they're all equal to a particular constant. So which means that if there's no arbitrage, this particular condition must be satisfied. Because of this condition here, let's rewrite our process in a different way. So let's write df is equal to mu times sigma g f times f dt, then sigma f dz, and rewrite our g process as well. Now, if we can see here, basically what we have done, we have used sigma g as lambda, and so then we have changed the mu f to r plus sigma g sigma f. So if we were to write it this way, we will satisfy this condition here, because here is sigma g. So mu f is equal to sigma g times sigma f plus r. So r plus sigma g times sigma f, which is exactly here, r plus sigma g times sigma f. Okay, so we have rewritten our process to ensure that we satisfied that no arbitrage condition here. So we basically says that if the mu satisfies a particular condition, really is the risk-free rate plus something here. This is like a risk premium for this particular process. And you actually see here really the interpretation of this is that sigma G is the risk premium and sigma F is the amount of risk that is going to be compensated. The amount of risk times the price of the risk. Amount of risk times the price of risk. The price of risk in the market is consistent, okay, which is lambda here. Lambda is basically the price of risk. Now, if you have this, what's going to happen here? Okay, so we have, in this case, used G as a reference product and sigma G as the price of risk. Then what can we say for the process that F divided by G? Okay, because we use G here, we want to know F divided by G. Now, it turns out F divided by G is equal to sigma F minus sigma G times F divided by G. So this new variable, F divided by G, is actually a martingale because the change of this thing here is unrelated to, I mean, we'll get it. It's unrelated to the things that the process was having before. It would this Z here has an expected value. The dz has an expected value of 0, and at any point in time, all those things are parameters, and so the change of this conditioned upon a value that was earlier is going to be 0. So the expected value of this as of the expected value of F divided by G at a future time conditioned upon the value of F divided by G at an earlier time would just be the value of F divided by G at that earlier time. So this F divided by G, a new variable, which is equal to F divided by G, is a martingale under some measure. To see how we derive this condition here, notice if we rewrite df this way and dg this way, we then, first of all, we do d log f by ethos lemma. We'll have this particular form here. Same thing for d log g. Then d log f minus log g is just this thing minus that, and which is then equal to log f minus log g is then just log f divided by g. So you have the process for log f divided by g like this. Now again, you apply ethos lemma. So you apply ethos lemma once here. Then you apply ethos lemma again here. So you will get the f divided by g. Basically, you take a function, you call this thing here, you take a variable, then the function will be e to the power of x. Okay, if this x, then the e to the power of x is the function. So then you, by ethos lemma again, log f divided by g is then sigma f divided minus sigma g times f divided by g dz. Okay, try that. Now, it's important to try this out because you will actually find later on applying ethos lemma several times in this particular fashion is actually very useful as a technique for us to solve many questions. So to try that and make sure you are able to do this. So we've shown this ratio F divided by G is a martingale under some measure. Now, when I say, what does it mean by under some measure? Because we have created this martingale by having sigma G as the price. So this is very dependent on what the denominator is, whether G is the denominator or whether F is the denominator. So if you look at G divided by F, then you cannot use sigma G as the risk premium as the price. You then, for that particular one, for G divided by F to be a martingale, you have to use sigma F as the risk price. Okay, so that's why this one being a martingale is under certain probability measures depending on how we determine the risk price. Now, if F divided by G, the ratio, is a martingale, then F naught divided by G naught, so it's basically the ratio of F divided by G at an earlier time, say time 0, is equal to the expected value of F divided by G at a future time big T. Now, this particular expectation here is dependent on which premium you select. By selecting a different risk premium, you have a different distribution. Because if you look at, you can think about that, the earlier examples where we draw this graph from the real world probability distribution to the risk neutral probability distribution, and the shifting of that probability density function is by the amount of risk premium. And so basically that shows if you use a different risk premium, you will move that in a different way. So the expectation is dependent upon which risk premium you are using, which means which one is the denominator. So the choice of the denominator is very important. And we call this denominator the numeraire asset. So you will hear that many, many times. So and later on, we will talk about if we were to change the numeraire asset, how do we recover the martingale. Now note, F by itself is not a martingale, G by itself is not a martingale. It's F divided by G, that ratio is a martingale, okay? And if you have F divided by G being a martingale, which means that F naught is equal to G naught times the expected value of Ft divided by Gt. Because it's basically this just an equivalent expression here. Now, this thing is very, very important because later on when you approach pricing, the first thing you want to do is try to think in this particular term here. You'll try to write something like this. If you are able to write this successfully, then you have gone a long way in terms of deriving the price of a security, of a derivative asset. And note that the ratio here, the ratio of these two assets at the earlier time is just the expected value or the expectation of a ratio at a later time. So all you need to do is to take an expectation. So you don't have to worry about anything else. Taking an expectation is easy. So if the only thing you need to do is to take an expectation, then it's very easy to provide or to derive pricing formulas. So here you will say that the value of G at time 0 is really the the value of F at an earlier time, the initial time F time 0 is really the price or the value of asset G at initial time times this expectation here. So typically you will be able to observe this and this. We are at time 0 here. You have an asset here G, and you want to figure out what the price of F. And so you have this relationship here. This is observed, and somehow if this expected value is an observed variable that somehow in the market you can observe that, then you can calculate this price here. Okay, so typically people wouldn't really ask you to figure out what this probability measure, and so then ask you to take an expectation under that probability measure. Typically that's not the case, because that typically is not observable. But in many situations you are able to observe this entire thing. This expected value is a particular variable that we can observe in the market. And if that is the case, then you can derive the price of F naught.